Okay guys, so in this video I'm going to run through the objectives for this week and hopefully also run through a sample quiz. So for each objective you have to get 3 questions in a row correct, so it is well worth taking your time and being very certain before you hit the submit button. So Alex really kind of brutalizes you if you rush through things, and it rewards you if you do sort of slow and steady work. So in this case, we want to be understanding the organization of the electromagnetic spectrum. So what we're going to want is we're going to want a diagram of the electromagnetic spectrum, and there's one in your book. I think it's image number 3 in this chapter. Let's see where it is. So here we go, in there, and there it is, just like I said, image number 3. And you can see that I've highlighted it, and then I've attached a little tag to it that says EM spectrum. And you can do that if you highlight something in your book, and then you get the option of leaving a little note beside it and giving it a particular color. So I kind of like to do that, and as I knew that this was figure 6.3 because of that. All right, but here's the important thing. The EM spectrum, in order of increasing wavelength, looks like this. At very low wavelengths, at very short wavelengths, we have gamma rays. Then we have X-rays. Then we have the UV region. And then we enter into the visible region, which is around about 400 to 700 nanometers. And that goes violet, indigo, blue, green, yellow, orange, red. And then beyond the visible, we have the infrared, followed by the microwave. And then there are a bunch of kind of divisions in here, but I'm just going to call them collectively radio waves. And that's all of your like FM radio, AM radio, radar, TV, things like that. Okay, so we have to list these in order of frequency, wavelength, and energy. So the important thing is that we've got increasing wavelength going left to right. We've got decreasing frequency and energy. And how those 3 things are related is like this. Energy of a photon is equal to Planck's constant times by the frequency, which is equal to hc on the wavelength. And the reason being because the frequency is equal to c on lambda. So I just substituted c on lambda into the first expression. So what you can see here is that energy goes up as frequency goes up as wavelength goes down. So energy and frequency are directly related. Wavelength and energy are indirectly or inversely related. Okay, so how does that help us? So let's list these guys in order of, we've got to make sure we've got the right one, increasing. So they're going to be in order of increasing. So and that means we're going to go from lowest to highest. So which of these guys has the lowest frequencies? We've got microwaves over here. Then we've got radio waves. Okay. Blue light, ultraviolet. So it's got to be radio, right? So it's going to go radio is the lowest frequency. And then microwaves. Yeah, radio, microwaves. Then keep going this way, blue light, number 3, keep going, ultraviolet, number 4. Okay, so what about in order of increasing wavelength? So the shortest wavelength is down here. Let's just head along. The first one we're going to hit is UV, so that's going to be number 1. We keep going. The next one we're going to hit is blue light, so that'll be number 2. Keep going. The next one we hit is microwaves. We're going to put that in at number 3. And then finally, the biggest wavelength will be radio waves. Okay, so what about energy? Well, energy and frequency will follow the same pattern. So we can just copy our numbers over from the first column. So 2, 4, 3, and 1. And there we go. So really it's just a matter of like not getting confused and making sure that you get the ranking in the correct order. People often get the ranking reversed, and you're going to need a image of or be able to reconstruct the electromagnetic spectrum. So some people didn't include that in their notes, and I pointed it out to them. Hey, you probably want to get a hold of one of these and make a note of where it is. Okay, so the next problem is about interconverting wavelength and frequency. So this is pretty simple because we know that the speed of light is equal to the wavelength of the light times by its frequency. So it's fairly easy to use this relationship to convert between wavelength and frequency because speed of light is a constant. Now there's often prefixes involved here, so keep in mind that if you go over into the data section in ALEX, the very first list that is provided to you is a list of SI prefixes, so you should never be getting those guys wrong. Just go into the data section and pull out the prefix that you need. So let's read the question. Humans have 3 types of cone cells in their eyes which are responsible for color vision. Each type absorbs a certain part of the visible spectrum. Suppose a particular cone cell absorbs light with a wavelength of 442 nanometers. Calculate the frequency. So this is all about calculating frequency. So I just got to reorganize here. C on wavelength equals frequency. And now I'm just going to do the math. Now something about frequency is that the SI units for frequency are per second or seconds to the -1, but it's important to realize that 1 wave per second is exactly the same as 1 hertz. So we can use hertz in place of per seconds if we want. So the speed of light, 2.998 times 10 to the 8 meters per second, divided by the wavelength, 442 times 10 to the -9 meters. Meters cancels out and gives me the frequency in per second. So we can just go ahead and do that. 2.998 by 10 to the 8 divided by 442 by 10 to the -9. Enter, and there we go. Now it said give your answer to 3 significant figures, so it's 6.78 by 10 to the 14. And you can use either per seconds or hertz for the units. And typically this is visible light. It's going to be down at the blue end of the spectrum. And they're typically around 10 to the 14 hertz, these photons. So we kind of know that we got it right there. Okay. So this is all about interconverting wavelength, frequency, and photon energy. So I gave the relationships previously. The energy of a photon is equal to Planck's constant times by its frequency, or alternatively we can say it's equal to Planck's constant times the speed of light divided by the wavelength. Now something to kind of keep in mind is you'll see it kind of gets a little tiresome entering in Planck's constant and the speed of light. The ALEX calculator has a bunch of the constants stored in it, so that can kind of often, like, online calculators where you're using the mouse to click the buttons are a little cumbersome, but it can actually be helpful in this case because you don't have to keep typing all those numbers in. Okay, so it says it takes 614 kilojoules per mole to break a carbon-carbon double bond. So if I break a whole mole, that's a triple bond, isn't it? Like a whole mole of carbon-to-carbon double bonds to give 2 moles of individual carbon atoms, the energy that I have to put in is 614 kilojoules. Now, what's going to happen is 1 bond will break every time 1 photon is absorbed. And what we're asked to calculate is what is the maximum wavelength of just the 1 photon to break 1 bond. Right? Now, maximum wavelength is just another way of saying the minimum energy that it has to have. All right? It's just that it's the same thing. So what we're going to do here is, it's one photon breaks one bond. So we need the energy of one bond. So we're going to take kilojoules per mole, and we're going to turn that into kilojoules per bond, right? Use Avogadro's number to do that. Then, we're going to turn that into joules per bond. I got half of that was written as moles and half was written as bond. Joules per bond. And then we're going to use this, and we're going to solve for the wavelength, right? To get the wavelength. Now, it doesn't ask for particular units for the wavelength. It says 3 significant figures. Now, UV light has enough energy to break chemical bonds, but visible light generally doesn't. So I'm expecting a wavelength that is less than about 400 nanometers. So anything smaller than that, I wouldn't expect this to be visible light. Visible light generally doesn't degrade chemical bonds unless it's a particularly sensitive bond. So I've got that in the back of my mind that it should be, a number smaller than 400 nanometers. So let's do this. 614 kilojoules for a whole mole of bonds. And then I know that in 1 mole, there's going to be 6.022 by 10 to the 23 bonds. Okay, so I've done that one. Now I want to turn this into joules, and I know that there are 10 to the 3 joules in 1 kilojoule. So that should get me to there. Let's just check that everything cancels. Yep, joules per bond, right? So I've got to where I wanted to get to. So I'm going to put that into my calculator and get my answer. So 614 times 1 on 6.022, second function E23, times 1 by 10 to the 3. All right, so this is good, and we want this to 3 sig figs, but I'm just going to write it down to 4 sig figs to begin with, so that would be 1.020 times 10 to the minus 18 joules. So that's the energy of the photon. We don't want the energy of the photon, we want the wavelength. So we know that E equals hc on lambda, which means that lambda is equal to hc on E. So I'm just going to go ahead and do that math now. I'm going to put my units in just to make sure that I've recorded the formula correctly, right? Because you don't want to be making errors. And then E 1.020 by 10 to the minus 18 joules. And to be just kind of be clear, typically energies of photons that we're dealing with that are absorbed by atoms and molecules are around about 10 to the minus 18, 10 to the minus 19 joules. They're the kind of energies involved. So joules cancels, seconds times seconds to the minus 1 cancels out, leaves with meters, which is good because I'm trying to calculate a wavelength. So here we go, 6.626 by 10 to the minus 34 times, you can see why it gets a little tiresome putting this in, 2.998 by 10 to the 8 divided by the answer that I got before. Enter. There we go. 3 sig figs, right? 1.95 by 10 to the minus 7 meters. And I'm going to turn that into nanometers just so I've got a kind of an easy reference. 1 nanometer is 10 to the minus 9 meters. There we go. And so then lambda is going to end up being 195 nanometers. And what did I say? It should be in the UV. And that is very firmly in the UV. All right, it should have been less than 400 nanometers, and it is. So feeling pretty good about that. Okay. So this is about calculating the wavelength of a spectral line from an energy diagram. So what we have to remember is this. We have the nucleus down here of an atom, which is positively charged, and then we have energy levels where the electrons are found, right? And so this is increasing energy going up there. Now, an electron, when it absorbs light, moves to a higher energy level, okay? And when an electron moves from a higher energy level to a lower energy level, it emits energy in the form of light. So that so atoms, or the electrons that are within atoms, gain and lose energy by emitting and absorbing light. Now, the bigger the distance that the electron moves, the more energy that is released, right? So this process here where this electron moved all the way up to the third state here, that's a lot more energy than when the electron moved from the fourth state down to the second state. So keep that in mind. Now there's a naming convention for these levels. One way is via this number, we call it the principal quantum number, the n value, n equals 2, n equals 3, n equals 4, and it's pretty simple. The lowest one is 1, and then it just increases in steps of 1. Okay, so the transition by that first arrow there would be from n equals 1 up to n equals 3. Okay, there's another way of labeling them, and that's with different names. We call the lowest level the ground state, and then anything that's above the ground state is labeled as being an excited state. Now you can see the difficulty already, the lack of clarity here is that you're going to end up with multiple excited states. So how do you know what one's what? And so what we do is we label them as being the first excited state, the second excited state, the third excited state, and so on. Now you can see a little bit of a problem in that the principal quantum number, this integer over here, doesn't line up with the numbering scheme of the excited states, and so sometimes that causes people a little bit of confusion, but you just have to be aware of it, okay? Alright, so what you're given is an energy diagram that shows the allowed energy levels of an electron in a certain atom, and they give you a little warning here because the energy is given in Z joules. So Z is the prefix for zepto, and it's equivalent to saying times 10 to the minus 21. Now, of course, you already knew where to look that up, right? Because I mentioned earlier about the little data button and then how it has a list of SI prefixes there. So you wouldn't have, and it prompts you as well. So you shouldn't have had any trouble. So we just want to be aware of that. So let's have a look at this energy diagram and see what everything is. So A is the lowest lying one. That's the ground state. Let's figure out the scale. So there's 200. And so we got 50, 100, 150, 200, 250, 300. So A is at 300. And then we've got B here, and B, it looks like it's one line below 600, so that's going to be at 550 zeptojoules. And then there's 1,000, and C is one line above, so it's going to be 1,050 zeptojoules. Okay, so that's the energy of the different levels, right? There they all are. So what is the energy of the electron in the ground state? So the ground state is the lowest lying one. So it's going to be 300, and you want to put a decimal on the end, 300 zeptojoules. Okay, then it says, what is the energy of the electron in the first excited state? So that's the ground state. It's going to be the first excited state. and that's going to be the second excited state. Okay, so the first excited state is 550. Then it says, if the electron makes the transition shown by the red arrow from C to B, will a photon be absorbed or emitted? Well, the electron is going from higher energy to lower energy, so that means that a photon has to be emitted. And the photon will carry that energy that is being lost. Okay? So this says, calculate the wavelength of the photon that would be absorbed or emitted. Round your answer to 3 significant digits. So lambda equals hc on E. So 6.626 times 10 to the minus 34 joules seconds times 2.998 by 10 to the 8 meters per second divided by the energy when it goes from 1050 to 550, so that equates to a loss of 500 zeptojoules. So we can do that, 1050 minus 550, because it's zeptojoules, we're going to do times 10 to the minus 21 joules. Here we go. All right, so what gets cancelled? Joules goes, seconds times seconds to the minus 1 goes. So there we are, what we're left with, meters. All right, so put all of that into my calculator, and I'm going to get a wavelength in meters. Now, I might convert that to nanometers or something similar, right? It actually asks, oh, there you go. It asks in the problem for it to be nanometers. So we will be converting it to nanometers. All right, we'll do that in a moment. Let's just do this bit first. All right, so Planck's constant, 6.626 by 10 to the minus 34 times the speed of light, 2.998 by 10 to the 8, divided by the energy, which was 500 zeptojoules. And there it is, right? Now we were asked to give it to 3 significant figures, so that's going to be 3.97 by 10 to the minus 7. 3.97 by 10 to the minus 7 meters. We'll turn that into nanometers. 1 nanometer, 10 to the minus 9 meters. So it's going to be 397 nanometers to 3 significant figures. And there's no rounding in there or anything weird like that. All right. So not too bad. Not too bad. The last one was a little bit. Okay, so it says predicting the qualitative features. So we're not going to be doing any math here. All right. Oh, that's nice. The energy diagram shows the allowed energy levels of an electron in a certain atom or molecule. What is the ground state? Well, the ground state is the lowest one, so it's going to be E. How many excited states are there? Well, we've got D and C, so that would be 2, right? How many lines are in the absorption spectrum? Ah, interesting. All right. So we could go from E to D. We could go from E all the way up to C, and we could go from D to C, and I can't see any others, so that would be 3 lines. Remember, when we're absorbing, we're going to a higher energy level. So I'm going to put 3 lines. And then it says, what transition causes the emission line? So emission is heading down, right, with the shortest wavelength. And shortest wavelength, that's equivalent to saying biggest energy, which is equivalent to saying the biggest distance that the electron moves. So if we're thinking about an electron moving downwards, what's the biggest distance that it could move? Well, it would have to be from C all the way down to E. So I'm going to put this in as C to E. Okay. Now, a lot of people were, copying answers from Chegg for these, and Alex randomizes the words, and it'll flip things like shortest, longest, emission, absorbance, and everything like that. So be really, really careful before you copy blindly an answer that you find online. Have a look at it. Use it. It's okay to use resources to kind of like guide you in how to answer questions or to kind of show you how stuff is done. But don't just copy it over assuming and carelessly, because they're often slightly incorrect. What transition causes the emission line at the longest wavelength? So longest wavelength, right, means smallest energy, which means the smallest movement, the smallest distance that the electron moves. Okay, now this is an emission line, so the electron is moving downwards. So if I look here, the shortest distance that an electron could move would have to be from D to E. Okay, so that one's going to be D to E. Yeah, that's good. All right, I only got one more example objective. This is calculating the wavelength of a line in the spectrum of hydrogen. Now, and it gives you the Bohr formula, all right? So it really wants you to use the Bohr formula. Now, they give the Rydberg energy the symbol uppercase R with the subscript Y. Your book uses K, all right? So just don't get confused by that. Now, if we go into the book, because I love highlighting things, right? Here's the Bohr formula here, and this actually, you can calculate the wavelength in one step here. Now, an alternative way of doing it is to use this formulation of the Bohr equation. Can you see that? 1 on the wavelength is equal to K on HC, 1 on N1 squared minus 1 on N2 squared, and N1 and N2 are just the two states that you're moving between. So what does K equal? Here it is here. See, I highlighted it, left a little tag on it, right? 2.179 by 10 to the minus 18 joules. So it wouldn't be bad to, let's just use this formula, and then I'll show you how to kind of very quickly get the wavelength. All right. So, wrong window. There we go. All right. So 1 on lambda was K on HC times by 1 on N1 squared minus 1 on N2 squared. All right, so I'm just using K instead of uppercase RY because most people use the lowercase k. Now we're going to be moving in this, it's an absorbance line, so we're moving up in energy from energy level 2 up to energy level 9. Now, when you use the Bohr equation, just remember that N1 needs to be less than N2, and you'll always get a positive number. And that's pretty easy to remember because 1 is less than 2, right? Okay, so that'll do that. Now, there's a real simple thing here that we can just do with this formula is let's just take the inverse of both sides, and you'll see now we just get the wavelength returned to us in the one step. So I'm just going to raise both sides to the power of -1, that is inverse both sides. So let's see what we got here. So the wavelength will be equal to K, which was 2.179 by 10 to the minus 18 joules, divided by Planck's constant, times by the speed of light. You can see here why it might be advantageous to use the calculator that has the built-in constants, can't you? And then we were going from the second level, so 1 on 2 squared, to the 9th level. There we go. It doesn't ask for particular units here, and then we've got to remember to invert it. Alright, so let's have a look here at our units. Joules goes, seconds times seconds to the -1 leaves 1 over meters, but then we're going to inverse it, so that's going to give me meters. Alright, let's put this into the calculator, and I'll show you how I do it. So 2.179 by 10 to the -18 divided by parentheses 6.626 by 10 to the -34 times 2.998 by 10 to the 8, close parentheses, open new parentheses, 1 on 2 squared minus 1 on 9 squared, close parentheses. I'm going to get that answer there. Okay, there it is, but I've got to do this to the power of the -1. So now x to the -1, boom, and there's my answer, right? Now it's set to give to 3 sig figs, so 3.84 by 10 to the -7 meters. Let's just turn that into nanometers now. 3.84 by 10 to the -7 meters times 1 nanometer is 10 to the -9 meters. And there we go, 384 nanometers, which is just into the UV, okay? Just into the UV. Okay, so we're looking at the quiz now, and we have an energy level diagram here. We can tell that it is a qualitative energy level diagram because the axis doesn't have any numbers on it. So what do we got here? We've got 3 energy levels. We've got the ground state there. We've got the first excited state, and we've got the second excited state. So it says, which is the ground state? Well, that's the lowest one, so that's A. And then there are 2 excited states, B and C. And then finally it says not finally, but before we start getting into the transitions, it asks how many lines are there in the absorption line spectrum. So absorption is when we're going up in energy. So we could go from A to B, we could go from A all the way up to C, and we could also go from B to C. So there are 3 lines. And then it asks what transition causes the emission line at the shortest wavelength. So keep in mind that emission means that we're going to head down in energy. So it's not going to begin with A, right? It's going to begin with B or C because we've got to be able to go down in energy. And then shortest wavelength means biggest energy, which means biggest distance. So heading down, what is the biggest distance I can travel? It's got to be C all the way down to A. So this one is going to be C to A. All right, so we've only got one left. It says, what transition causes the emission line at the longest wavelength? So emission is heading down, and longest wavelength means smallest energy, which means smallest distance. So for those 3 levels, what's the smallest distance I can travel heading downwards? And it's got to be from C down to B, right? That's the smallest spacing between any 2 lines. Okay, not too bad. Just got to be slow and careful. Okay, this looks like it's ranking things in order of wavelength. Okay, so whenever you're ranking, you always want to make sure that you don't get the order reversed by accident. A few different types of electromagnetic radiation are listed in the table below, so you can look at figure 6.3 in the book, or you can kind of make your own EM spectrum. And then we know in visible it goes violet, indigo, blue, yellow, orange. Oh, we missed out green, didn't we? It's weird writing it backwards, right? Because you're normally used to thinking about it as Roy G. Biv. Okay, there we are. Finally got the right order. So we're asked to list this. For example, select increasing wavelength. So this is increasing wavelength this way. Okay, so we want 1 for the longest, for the shortest, and then 2, 3, 4 increasing wavelength. Okay, so yeah, okay, just making sure we got that right. So we're going to go this way and see what we encounter first. Gamma rays, there's no gamma rays. X-rays, there's no X-rays. UV, there's no UV. Now we're going to get into some colored ones. Violet, there's no violet. Indigo, there's no indigo. Blue, there's no blue. Green. Green is going to be our longest wavelength. There it is. So that's going to be number 1. And then we're going to keep going. Yellow, there's no yellow. Orange, there's no orange. Red. Red is going to be our number 2. Infrared, that's going to be our number 3. And then, yep, radio waves is going to be our number 4. So it's 1, 4, 2, 3. So you just got to be careful not to make a mistake. Remember, figure 6.3 in your book has the EM spectrum. Okay, it looks like another qualitative energy diagram, doesn't it? Again, we know it's qualitative because there's no units on the axes. Okay, so this time we've got 4 energy levels. A is going to be our ground state, and then we've got our 3 excited states, right? So first excited state, second excited state, third excited state. So what is the ground state? Well, A. How many excited states are there? Well, we've got B, C, and D, so that is 3. And then how many lines are in the absorption spectrum? So remember, absorption is going up. So we could go from A to B, that's fairly small. We could go from A to C. We could go from A all the way up to D. So that's all the ones that originate at A. And then we could go from B up to C. And then we could also go from B all the way up to D. And then finally, we've only got one that originates at C. We could go from C all the way up to D. So if you add all of that up, we've got 1, 2, 3, 4, 5, 6 possible lines in the absorbance. Okay. And then now it says which transition causes the absorbance line at the shortest wavelength. So lambda, the shortest, is the biggest energy. And that means it is the biggest distance that the electron moves. And for absorbance, we're going up, right? So if we look at all of this guy, what's the biggest distance that an electron can move upwards? Well, it would be from A all the way up to the third excited state, D. So it's going to be A to D. Okay, and then it asks what transition causes the absorbance line at the longest wavelength. So again, absorbance is going up, and lambda longest means the smallest energy, which means the smallest distance that is moved upwards, right? So, what is the smallest distance that you can move? And by my eyes, it's pretty obvious that the smallest distance you could go would be from A through to B. There we go. So that would be the least energetic transition. Okay, let's have a look at this one. So this is about using the Bohr formula. So we know that Ry is the same as what your book labels as K, which is 2.179 by 10 to the minus 18 joules. And you can flip on over to your book, and there it is there. Okay, and like I said, I highlight these things so I don't have to keep looking them up every time. Got them on hand. All right, so what are we asked to do? It says in this equation, Ry stands for the Rydberg equation, N stands for the principal quantum number of the orbital that holds the electron. Yep. You can get the value for the Rydberg energy using the data button. Yep. Calculate the wavelength of the line in the absorbance line spectrum caused by a transition from n equals 4 up to n equals 9. So remember, I like to use the expression that's given in the book, right? Which is, I'll just pop it up here. This one here, 1 on lambda is k on hc, 1 on n1 squared minus 1 on n2 squared. Remember that n1 is the smaller value, n2 is the bigger value. So that's what we're going to do. And then if we take the inverse of that, just by raising everything to the power of minus 1, we'll get our wavelength directly. Now that'll give us the wavelength in meters. So what we'll need to do is we'll need to turn that into, in this case it wants micrometers to 3 significant figures. So we'll have to do a little bit of, finagling to get it into micrometers. So let's write it out with all of our units because we want to show our instructor that we know what we're doing. And also it's easy to enter this into the calculator incorrectly. In fact, the first time I demonstrated this problem, I have a little confession here, I did enter this into the calculator incorrectly, and I knew, and we're going from 4 to 9, and I knew I'd got it wrong because I got a stupid answer. And then everything to the minus 1. So that's what needs to go into the calculator. Like I said previously, it can speed things up if you use the calculator that's got the values stored. So let's see how we got. So I'm going to do this all in one go. Parentheses 2.179 by 10 to the minus 18 divide parentheses 6.626 by 10 to the minus 34. It's Planck's constant times the speed of light. Close parentheses times new parentheses 1 on 4 squared minus 1 on 9 squared. Close parentheses, close my last parentheses to the minus 1. Whew! Ah! No! And something went wrong, didn't it? We probably were missing some parentheses there. All right. Take a deep breath, go again. 2.179 by 10 to the minus 18 divide Planck's constant times the speed of light, close the parentheses, new parentheses, 1 on 4 squared minus 1 on 9 squared, close parentheses, enter, then to the minus 1, and there it is in meters. All right, okay, so that's my answer in meters. We wanted 3 significant figures, so it's going to be 1.82 by 10 to the minus 6 meters, and we were asked to express this in micrometers. So 1 micrometer is 10 to the minus 6 meters. And so you can see 10 to the minus 6 just cancels out, and we've got 1.82 micrometers to 3 significant figures. All right, so despite my incompetence with the calculator, we did eventually get there. All right, this is interesting. Infrared radiation from young stars can pass through heavy dust clouds, so allowing astronomers here on Earth to study the earliest stages of star formation before a star begins to emit visible light. So what's going to happen is this. I'm actually kind of like an amateur astronomer. You have some matter that is kind of gathering, forming a cloud of dust, right? And it's the first part of like star formation. It's just kind of like this loose gathering of matter. And then light from another star is going to be coming at it, right? And that light's going to be of, different colors. And what's going to happen is, depending on what that gas cloud is made of, some of those colors are going to get absorbed and won't appear on the other side of it, right? So that's basically how we can tell what the composition of this dust cloud is, by looking at the light that passes through it, right? So if you can look at the light, behind the dust cloud, and then on the other side of the dust cloud, so you've got a star over here, you look directly at the star, and then you look over here, you can see what matter that light has passed through. It's pretty cool, right? So suppose an infrared telescope is tuned to detect infrared radiation with a frequency of 4.06 terahertz. Okay, so we're going to have to look up the prefix for tera in the data section, and tera just means times 10 to the 12, okay? And what we're going to have to do is turn this frequency into a wavelength, and they want the wavelength in micrometers, and 3 sig figs. So this is pretty easy, right? We know that the wavelength and the frequency are just related via that expression. So if we want the wavelength, it's just going to be C on the frequency, but we just got to get everything in the correct units. So 2.998 by 10 to the 8 meters per second divided by, and then the frequency here, 4.06 times 10 to the 12 hertz, which is the same as seconds to the minus 1. So you can see that seconds to the minus 1 cancels out. Now, they don't want it in meters, they want it in micrometers. So we have to remember that 1 micrometer is 10 to the 6 meters. And then there we are, we've got our wavelength in micrometers. So our wavelength in micrometers to 3 significant figures, let's do it, 2.998 by 10 to the 8 divided by 4.06 by 10 to the 12 times 1 on 1 by 10 to the, almost made a mistake here, it's minus, isn't it? There we go. Please don't pick that up. That would have been megameters that I was turning this into. Minus 6. 1 micrometer is 10 to the minus 6 meters. There we go. Really close. 73.8. 73.8 micrometers. Good catch there, figuring that out. All right. Okay, 2 questions left. Let's see what we've got. X-rays have a wavelength small enough to image individual atoms, but are challenging to detect because of their typical frequency. Suppose an X-ray camera uses X-rays with a wavelength of 2.64 nanometers. Calculate the frequency of the X-rays, round your answer to 3 significant figures, and we're asked to give it in P hertz, capital P. So what is capital P? What is that prefix? That's for pico, right? And pico is 10 to the minus 12, okay? So I can't, let me see if I can bring that up for you, just to show you. You go into the data section. If you're ever worrying about these prefixes, just make sure that we get them right. Oh, actually, no, got to be careful. Pico is lowercase p, peta is uppercase p. There we go. Oh, 2 errors in a row. So that's 10 to the 15. Good catch. Good job on that. See the difference in the case? These are like, we don't use these very often, these prefixes, so always check them. Peta, 10 to the 15. Okay. So it's not, uppercase P is peta, and it means times 10 to the 15. So that's going to be useful. All right. So C equals lambda times frequency. We're turning a wavelength into frequency, C on lambda. So it's 2.998 by 10 to the 8 meters per second. And then the wavelength is 2.64 by 10 to the minus 9 meters. So meters go, gives me seconds to the minus 1, which is the same as hertz. So let's grab our calculator. 2.998 by 10 to the 8, that's the speed of light, divided by 2.64 by 10 to the minus 9. There we go. So we want 3 sig figs here, 1.14 by 10 to the 17 seconds to the minus 1. And hopefully by now you know that seconds to the minus 1 is the same as hertz, right? Now, we don't want it in hertz, we want it in these petahertz. 1.14 by 10 to the 17 hertz times by 1 petahertz is the same as 10 to the 15 hertz. So it kind of makes sense why they were doing this now, because it's going to give us a nice kind of number without an exponent, right? So times 1 divide 1 by 10 to the 15. That'll do the trick. 114 petahertz, right? 114 petahertz. I'm going to have to be careful about that because peta is not a common unit. So, yeah, I confused it with pico. All right. Okay, this looks like it's a ranking one, but there's lots of ranking going on. We have to rank in order of frequency, wavelength, and energy. So, and let's just do that. We've got gamma, X, UV, then we got our visible, which is a range of stuff, isn't it? Then we got IR, microwave, radio, and then within the visible we've got violet, indigo, blue, green, yellow, orange, red. Hey, I got it right that time. And then if we're going to go this way, what are we going to get? We're going to get increasing wavelength, but we're going to get decreasing frequency and energy. Now, if we rank something in order of frequency, we're going to have the same ranking in order of energy, because remember that energy is just equal to Planck's constant times by the frequency. So really this problem looks like you're doing 3 things, but once you've got the order of frequency, you also are going to, that's going to be the same order for the energy. So increasing, we're asked to rank these in order of increasing frequency, wavelength, and energy. So increasing energy or increasing frequency is going to be going right to left. So what do we got? We're going to head along through here. Do we have radio waves? No. Do we have microwaves? No. Do we have infrared? Yes. So infrared is going to be our lowest frequency. So that's going to be 1. Do we have red? Yes, we do. So that's going to be number 2. Do we have orange? No. Do we have yellow? No. Do we have green? No. Do we have blue? Yes, we do. So that's going to be number 3. And, you know, do we have indigo? Do we have violet? Do we have UV? Do we have X-rays? Yes, we have X-rays. So that's going to be number 4. So 1, 2, 3, 4. There we go. That's interesting. And so that's going to be also the energy, the order of energy. All right. There we are. So now we just got to do order of increasing wavelength, and we want to go left to right this time. Do we have gamma rays? No. Do we have X-rays? No. Do we have U? Oh, yes, we do. X-rays, yes. So that's going to be 1. There we are. Do we have UV? No. Do we have violet? No. Do we have indigo? No. Do we have blue? Yes. So that's going to be number 2. Do we have green? No. Do we have yellow? No. Do we have orange? No. Do we have red? Yes, we do. That's going to be number 3. And so there's only one left. Do we have infrared? Yes, we do. And so that's going to be number 4. All right. So, you know, by doing, by not sort of like trying to work backwards from the frequency to the wavelength, by actually working across the EM spectrum, that's a good way of avoiding making errors. Okay, so that's it. We went through all of the objectives and we went through a practice quiz, and I hope that that is helpful. And yeah, good luck with everything, and let me know if there's anything I can do to help you get ready for the quiz.